One of the most interesting aspects of nuclear chemistry is the energies involved in nuclear transformations. In this video, we're going to take a first look at how those energies emerge, and then we're going to use some concepts to try to understand the thermodynamic stability of a variety of nuclei. Our starting point is going to be imagined reaction in which we're going to generate an atom of oxygen-16 from the nucleons of that atom. Right? So notice that oxygen-16 has 8 protons and 8 neutrons. Okay, so here's the neutrons, mass number but no atomic number, and here's the protons, which contribute both to the atomic number and to the mass number. Okay, so we're going to try to calculate what would be the energy involved in this hypothetical process. The way to do this is to recognize that there's actually a slight difference in the mass between reagents and products. We know that the mass of one neutron is equal to 1.675 10 to the minus 26 kilograms. The mass of one proton is equal to almost the same, slightly less, minus 26 kilograms. Right, so we can actually take then 8 neutrons and 8 protons and multiply those masses, add them up, and then what we will find is that the mass that you would expect to find out of this for one atom of oxygen would be equal to 2.6784 10 to the minus 26 kilograms. Right, that is what you would expect to find if mass was conserved. But as it turns out, in these processes, mass is not conserved. Okay, now you can take those atoms of oxygen-16, put them through a mass spec, and then figure out what the exact mass of one of those atoms is. And we appreciate that in reality, there's a slight difference in the mass. That mass that you measured with the mass spec is 2.6554 10 to the minus 26 kilograms. Okay, so clearly mass is not conserved in these processes. As a matter of fact, what has happened in this nuclear synthetic process is that there's some mass loss that has happened. All right, so it turns out that that mass loss can be connected with an energy using the famous Einstein formula, right? Energy and mass are equivalent. Okay, so one of the things that we can do then is use this change in mass that we experience in this chemical reaction unrelated to the energy that has been involved in this particular process, right? We can change this to simply the change in mass over the change in energy, and then we take the difference of these masses, plug it here, multiply by the speed of light squared, and what we find is that delta E happens to be a ridiculously large number. It's going to be minus 2.07 10 to the minus 11 joules. Okay, this is negative, which is important because that means that energy is released as in this reaction. All right, so the reaction takes place, there's a loss of mass, and that loss of mass is invested in releasing energy that you can then harness for your own benefit. Okay, again, what I'm trying to say here is that this amount of energy is ludicrously large. Okay, even though we have a small exponent right here, of course we can change this to a more common measure of energy in chemistry, which will be kilojoules per mole. And when you do that, this number happens to be minus 1.24 10 to the 10 kilojoules per mole. All right, and that's what is very ludicrous, right? When we think about transformations in chemistry, when you're thinking about the energy involved in chemical reactions, that is usually on the order of maybe a few kJ per mole to a few hundred kJ per mole, right? So even in the most energetic chemical reactions, where you're simply just rearranging atoms, but not changing the atoms themselves, okay, these nuclear processes actually have about millions to tens of millions more energy than those that are in common chemistry. So obviously this is interesting for power generation and so forth, as it's well known. Right, so what we can then do is take stable isotopes and try to compare how the energies that are released in these processes compare between nuclei. Okay, what we can actually say is turn this on its head and say that, well, if you actually want to decompose those very stable nuclei into the constituent nuclear particles, then you will need to supply this huge amount of energy. Okay, so this is what we actually call the binding energy of those nuclear particles in the nucleus. Right, so the question is, how does this compare on a per nucleon basis, okay, across the periodic table? Right, so what we do is we do this table processes for every single nucleus, and then we divide that number over the sum of neutrons and protons, that's the number of nucleons, in order to get a normalized energy per nucleon that is we can compare across isotopes in the periodic table. And then what you find when you make that comparison is that the isotopes are distributed like this, right? So if we put in the y-axis binding energy, which is a measure of the stability of those atoms, okay, as a function of the mass number, A, what we find is that the graph looks like this, more or less. Right, so here, the most stable nucleus that we know is iron, 56. Right, so here would be a large mass number, so up here you would have your uranium, 238 and so forth. And then here you would have your low mass number like helium, and that's that, right? So here we have that again. On a per nucleon basis, the most stable nucleus can be or is iron. And again, we know that by carrying out these calculations of the synthesis of a particular nucleus from the neutrons and protons that are in that nucleus. Right, so in this video we have taken a first approach towards the thermodynamic stability of nuclei, and then we've seen that the energies involved in the nuclear process are much, much greater, millions of times greater than the typical energies involved in chemical reactions.